Now, let us talk about the stress strain diagram in metals in tension. Okay. So, this is a textbook drawing from Gears. Now, you can see here, this is how the blue curve here is how a typical stress strain diagram would look like for a metal. And here, when the initial area is used in the stress calculation, so on the vertical axis you have stress and on the abscissa you have strain. Now, when you calculate the stress, assume that this is a specimen on the right side, it is a steel specimen, we usually call it a coupon specimen. So, it is a flat piece, the cross section would be something like this, okay, or you can take circular, whatever it is. So, typically it is a flat coupon specimen. Now, here in the initial area is known. So, let us say, okay. So, here the cross section area is like this, and here cross section area is like this, and here it is a much thinner cross section area. So, the necking is happening there. Okay. Now, when the initial area of the specimen is considered to calculate the stress. What is stress? Stress is force divided by the area. Okay, that is how we calculate the stress. Now, if for that calculation, if you use the initial cross sectional area of the specimen, that is this area here, if you use that, then as after some tension is applied, the material's cross section can change, it can reduce with something called necking can happen here, and in that process what will happen is the actual stress which is observed is actually not used in the calculation, because the area change and it is very difficult to get that change in the area during the testing. So, there is an engineering practice which is use the original area, and we call that engineering stress. That is what this is here, engineering stress. So, how do we get? So, you put the specimen in the testing machine, you pull it, and then you keep on applying load, and then you calculate the stress corresponding to that load, and that stress is nothing but the force divided by the area. Okay, whatever the force you are applying by the original area, I am going to call it A0 here, we do not change that. Okay. So, that is what the stress is calculated, and this blue curve here follows that. Now, if the actual stress at every point of time is considered, then it will follow this curve. So, that is true stress, not the engineering stress, but the true stress. But how do we get the actual area during the testing? It is quite difficult to do, because it is difficult to measure that during the test. So, what we do in most of the testing, we will use only A0, and then we use engineering stress for a parameter for comparison of various materials. Now, let us see with different points or portions in this stress strain graph here. So, here is the origin, that is the point of application at the beginning, and then you have a point A which is called proportional limit. That means up to point A from O, it is a straight line. Okay, it follows Hooke's law. So, it is a straight line, and then at point B is where we call it is yield strength. So, after B you can see there is a flat region which is yield plateau, and so from after C, so this is from B to C, the material is perfectly plastic or yielding, material is yielding without really experiencing more stress. But after point C, it experiences more stress, so that we call this region strain hardening, okay, from C to D, and at D something like necking happens. So, that is this I have shown here, this is what is necking. So, why necking? Because at that neck region you have very small area or comparatively less area than the remaining section. So, that region has strained so much that now it is started necking. So, neck is the portion where you have smallest cross section even on our body, right. So, maybe that is the reason why we started calling it neck, it looks like that, neck of the specimen. And then finally, you have a fracture point which is E. At that point, the material breaks into two. Okay. Now, we look at how stress strain graphs of different materials would look like. Say, so here we can say this is from Mumlock and Zanowski book. So, you can say here figure 1.2 in that book. Now, identify difference between the following stress strain diagrams. So, here the first one you can look at it, and that is either for a glass or a chalk. So, you take a chalk piece, you try to pull it will suddenly break without any deformation, or there is no ductile behavior in that. That means that when you draw a stress strain graph, a straight line, and then suddenly the material breaks there. There is no ductility at all. Imagine you take a chalk piece and pull it, it will just break. It is not going to reduce the diameter of the chalk, etc. It just breaks, right. Now, in case of a steel, if you take steel and try to pull it using a machine or whatever, it will not break suddenly like in the case of glass or chalk, like in figure A. In case of B, where steel is used, that will have some ductility which is indicated by this portion here. Okay. Now, that means here you have elastic deformation, and then you have yielding, and then you can very clearly see ductile region in that graph. So, this portion indicates the ductile region. Now, in case of aluminum, again you will have ductility. One thing I want to tell you here in this slide, you notice that none of the pictures or none of the sketches here, diagrams, have any number on it. So, it is not that all are of same height and width and all that, they are of different magnitudes, but the general trend of the sketch of the graph is going to be like this. Don't compare the size of one graph to the other, just look at the trend or the shape of the graph from one to the other. Okay. So, in case of aluminum, you can see a gradual change in the curvature in the curve is gradually changing, whereas in case of steel over here there is a relatively sharp change. So, the yield point is better defined in case of steel, and yield point in case of aluminum alloy is not well defined. You have a gradual transition, that is mainly because of the alloys in that, because alloys means whether a different type of bonds, different so in the microstructure level, as you pull or as you apply the stress, there will be movement of dislocations, and bonds are of different type. All these will lead to, we will talk about this later in coming sections, but because of that there is a gradual change in the gradual transition from the straight line to a curvature. So, that yield point is not well defined in case of alloys. Now, in case of concrete, also similar case, you have a different variety of different materials in the concrete. So, there is no well defined yield point in case of concrete also, and also this linear region is not that long as compared to that in the steel. But again, this graph is for compression for concrete, that is also important. Then you have rubber. When you pull rubber, you can see that initially there is a change in the curvature also. You see here, and then the curve comes down like this, and then again goes up like this. Okay. So, that is indicating initially the rubber will take some load, and then it try to straighten all the molecules or chains in that, and then after some time you start seeing the strain hardening behavior in the rubber. Now, you can look at compare elasticity of all these materials, elasticity, brittleness, ductility, all that you can compare, and these are very important to look at while choosing a material. Now, elastic behavior for a homogeneous isotropic and linear elastic and axially loaded material, the modulus of elasticity can be, so for a material has to be very homogeneous. Otherwise, like I showed in the previous slide, if it is not like concrete, there is no straight line available for. So, in this case here, straight line is only for this much, maybe for concrete. So, it is not homogeneous as it's not as homogeneous as steel. In case of steel, you have a very long straight portion. Okay. So, homogeneous and isotropic means same property in all directions, linear elastic, linear, okay, and axially loaded material. The modulus can be defined as normal stress divided by normal strain. That is a material property. It does not change as a function of the cross section of the specimen which you use to test, and Poisson's ratio is negative of lateral strain divided by the longitudinal strain. Now, you can see in this picture here, you can see a person is pulling that blue strip, and as you pull, the length or the longitudinal strain is more, length is increasing and the width of the specimen is or of the strip is decreasing, and because one is increasing, the other is decreasing, that is why we introduce this negative sign here in the numerator of the Poisson's ratio. Now, how the Poisson's ratio, what is the range? Like it goes typically it is from 0 to 0.5, and for compressible material it is close to 0 and incompressible material is close to 0.5. Okay. Now, we can look at how these numbers are for steel, concrete, glass, etc. Here is a table which shows Poisson's ratio, the range for various materials, both Poisson's ratio and modulus. So, you can see aluminum modulus ranges from 69 to 75 GPa, whereas Poisson's ratio is typically 0.33. In case of steel, you can say the modulus is about 200, most of the steel which is about 200, and Poisson's ratio is 0.2. So, now in case of concrete, the modulus has significant variation, 14 to above 40, even we have today modulus concrete with more than that, or 40 also, and the Poisson's ratio is also significantly varying from 0.11 to 0.21. So, the point here is these properties also can vary depending on the homogeneity of the material, depending on various properties. Okay. So, these two are key material properties of any material which we consider for use in construction, and when I say they are material properties, what it means is that they are not dependent on the geometry of the specimen. Now, elastic behavior, also we have to look at the three-dimensional behavior. There is a generalized Hooke's law, which you can see in these three equations of over here, there only E and Poisson's ratio are material properties. So, I can calculate what is the strain in a particular direction if I know the stress applied in all three directions. Okay. So, with immaterial of the shape, so I can calculate the strain using the stress applied and the material properties like elastic modulus and Poisson's ratio. So, that is mainly the idea in this slide here. Now, when you look at stress strain behavior, you can see sometimes the graph look like a straight line, sometimes curved like this on the second. So, for linear material, the graph will be like a straight line like this, the first one. And for elastic behavior you can have elasticity, but it need not be linear all the time. So, there could be sometimes the graphs like this, curved graph like this also. So, question is, are both these linear? Answer is no. Okay. First one is linear, second one is not linear, or it is a non-linear. And are both these elastic? Okay. Both are elastic. So, do not say elasticity is only dependent on linear graphs or a non-linear graph also. Like in other words, in the second graph, the first arrow, this arrow here, that indicates the loading time. So, I load the material, okay, let us see if I load it like this, and when I unload it, if that follow the same path in coming back, then we can say it is a elastic material. In other words, it means it retains the original shape, or it comes back to its original point, okay, when the load is removed, or in other words, there is no permanent strain which happened during the loading and unloading process. If that is the case, then we can say it is elastic. So, it returns, in case of elastic behavior, it returns to the original shape when the load is removed and reacts instantaneously to the change in load. Instantaneously means the moment you release the load, it reacts immediately. There is no time lag between that. Okay. If there is a time lag, then we call it something called viscoelastic behavior. We will talk about that later. So, here it is elastic behavior. Now, how do we get some numbers for design purpose based on this elastic? So, there are different moduli which we consider: initial tangent modulus, then secant modulus, chord modulus, and tangent modulus. So, this is S, C and T. Okay. Now, how do we choose a material considering all this? So, that depends on the stress or strain level at which the material is being used. So, when we get this stress strain graph, so you can see the stress strain graph here, this thick black line. Okay. Now, when you have a stress strain graph of a material, and if you know in service what is the typical stress level that the material will go through, or based on the loads which are applied. So, I can calculate that in service stress level, and then I can use that value and these type of curves from different materials to compare. So, for example, if I want to design, I can say that secant modulus, I will use this point here, this is my stress level which I will consider. Okay. Then what you do is you get one curve like this, and maybe another curve will be something like this. So, you take this value and something like that, and for a third material the curve may be something like this, for then you compare this value. So, you can get the strain, corresponding strain in 3 cases. Okay. So, based on that you can decide what would be the strain experienced by the material if my option A, B and C, 3 options which I draw 3 vertical lines here. So, like that you can get the stress strain behavior, stress strain graph of various materials which are available for use, then decide the stress level which will be experienced by the material and while in use, and then based on that you can decide which material to take, whether the strain is beyond the limit or not. In this case, maybe I will go with, if my limiting strain value is here, then I can pick either this or this, but not the third one. Okay. So, if I say this is A, material B and that material C. So, if my limit is here, that is limit, I am going to call it epsilon limit is here, then I can say A or B are fine, but not C. Okay. So, these are some of the uses. So, like this we can decide the values for, or compare the values, chord modulus, tangent modulus, all these different moduli we can use and then compare all that. Now, elastic deformation under axial tension. So, atomic bonds stretch and stretch is recovered, and the stretch is recovered when we talk about elasticity. What is actually happening? Look at the first image here, where you have all these circles can be thought as an atom, and they are bonded. So, every line you have a atom in every line, 1, 2, 3, 4 atoms in first line, 4 here, 4 here, 4 here, 4 here. Okay. Now, this is the first is the case with no load, that means F is equal to 0, there is no load here. Now, in the second drawing, there is some load which is applied. So, you can see that this point here has changed from a square to a rectangle. That means the vertical lines over here, there is a stretching happening in the vertical direction. Okay. So, you can see the gap in between, these have increased, okay, between this this gap here, this gap here, this gap here, all that gap, the vertical gap has increased between each layer of the atoms. So, that is indicating that bond has stretched. Now, when you release the load, again the F is equal to 0 here, when you release the load, again that distance between the individual layers, the 5 layers of atoms have come back to the original shape. So, again it has become square. So, from square to rectangle to back to square. Okay. So, that means there is no residual strain after the load is removed, means the system has regained its original shape. So, this is a very good example for, or this is what happens when we talk about elastic behavior, okay, or elastic deformation. It deforms under the load, and when the load is removed, it goes back to its original shape. Now, we will see whatever I showed her in the previous slide, that is this part here, okay, elastic region or initial elastic region, where you can see that in this sketch here 3 and 4. So, you have to monitor where the positioning of 3 and 4, the relative position of 3 and 4 is in this whole sketch here. So, after this point, when the load is continuously the load is applied, more and more load is applied, stress is increasing, and there is some slip happens. So, you can see here the 4 has slipped down to the lower layer. Okay. Now, this kind of behavior, this is slipping. In the previous slide, we were talking about stretching of the atomic bond. Here, what is happening is slipping of the atoms from one layer to the other. When it slips, it does not go back to its original position. So, even after the load is removed, right, this point here, you can see that there is that 4 is not going back to the first layer. Okay. So, slip is permanent, but stretching is not really permanent. So, here atoms slip and then they stay there itself, they do not come back to their original position. So, that is why we have permanent deformation in the material. So, this is typically you can see this picture photograph here, where that inclined shape or cup and cone behavior, it is mainly because of this slipping happening in about 45 degrees in typical cases. Okay. Now, from this sketch we can get the plastic strain, that epsilon p here indicates a plastic strain. That means that much deformation is permanent deformation. Okay. Even after unloading, it does not come back to the origin of the curve. So, that is the permanent deformation. Now, how to get or estimate the yield strength? So, there is one method which is widely used, we call offset method. There is another method which is called extension method. I am not going to cover that here. In the offset method, we use this method for most applications. Now, what is yield strength? It is the stress. From the stress strain graph, we can get a stress value where the stress strain curve deviates from linearity. So, like this here, from here until here it is a straight line, and then this point it starts deviating. Okay. So, you have a proportional limit, you have an elastic limit, and then, but these two proportional limit, if you take, in this is a very good textbook drawing, but when you do actual testing in laboratories, you may not get a perfect curve which looks like this. Okay. And also there is no sharp change in the curvature. So, there is a gradual change. So, what will happen, it is difficult, you have to fix a point. So, to standardize the procedure, people have used some values like this 0.2%. Okay. For steel, it is used, offset is 0.2% for steel in tension, as you see in this table. For other materials, different numbers are proposed. Okay. So, anyway, let us look at this graph here, 0.2% you take for steel, and so you draw 0.2% is here, and then draw a parallel line to the original curve, and wherever that curve hits this point here, on the top right, and that is the, and the value corresponding to that, this one here, that we call as yield stress or yield strength. Okay. So, this is the point which is of importance, okay, on the, that is a yield strength. So, that is the value which we use for design purpose and not the value over here, not this, but the higher number which is more conservative also, okay, for the design purpose. I mean, it is not really more conservative, but that is a better way, that is what is being used. I should not say that it is conservative in nature. Okay. Now, there are different types of elastoplastic behavior. So, you can see here in the first one, this is typically for steel or any alloy, it will look something like this, where the example of loading and unloading, so it graph goes like this and then it comes back, and then if you load it again, it goes back and then follows like this. Okay. So, here you have plastic strain and then elastic strain. Okay. Now, second one, elastic and then perfectly plastic. So, this is the elastic region, okay, and then it goes back and then perfectly, this goes flat. Okay. So, that means perfectly plastic, and then elasto and then plastic with strain hardening. So, here it is a elastic region, it comes back and then plastic with strain hardening. Okay. Strain hardening means, why I am saying so, because there is also stress is increasing after that point. In this case, the stress is not increasing, only strain is increasing in the second case. Okay. That is a perfectly plastic scenario. Okay. Now, strain hardening is done during the manufacturing of cold form steel, because in the earlier time hot rolled steel was used, and that did not have very high strength, around 250 was the typical yield strength which was possible to achieve with hot rolled steel. So, there was a demand for higher strength steel. When I say higher strength, I mean high yield strength steel, HYSD. Okay. There was a demand for high yield strength deformed steel, okay, HYSD. So, what the industry did was, they used this strain hardening technology. So, what they did, they strain hardened the steel or cold rolled the steel when the temperature was below the recrystallization temperature. At that point itself, they strain the steel so that when this final product, the steel product will have a curve like this, okay, whereas the original curve is something like this. This is the original curve, the dashed portion on the second sketch. So, the first sketch shows elastic region, then stable necking, and then the strain hardening happens. In the second one, you are actually translating the graph to the left side. So, you can see here, basically if the steel is cold rolled steel or cold form steel, when you do the tension test, it will behave like this, will be the curve which you get, stress strain graph. So, this portion, this dash portion will be missing. Now, you look at the, compare the yield will limit, here it is here, you can see here, or I do not need this. So, you can compare, this much is extra which you gain, this much is the extra yield strength which you gain. Okay. So, that is the advantage of going for cold form steel with the same material properties, everything. You strain harden the steel, I mean a little during the manufacturing itself, so that you get a higher yield strength at the construction site, okay, or the final product which is used in concrete will have a higher yield strength. So, there is no change in the chemical composition of the steel, that is important to note down here. Okay. It is just the procedure of manufacturing procedure which is changed, so that the yield strength of the steel is more. Now, strain hardening, this is an example which you may want to practice. You take a paper clip and try to open the paper clip, Okay, once you open it, you do it. So, this is the paper clip and you open it like this, and then what happens is when you open it and you will see that you will not be able to keep it straight like this here. It is very difficult because the bent portion is already having. So, here this point here is having less strength than this point here, because that is already bent. So, when you try to straighten it, the bent portion is not getting straight, but the point adjacent to that is getting straightened, because the points adjacent to that is stronger. In other words, this point is weaker. This point and this point are weaker than this point which is already bent. So, when you try to straighten it, it will get straightened on the. So, the bent point does not get straightened that easily. Okay. In case of polymers, what happens when you do tension test? So, the curve might look something like this. Okay, I showed this earlier also. So, this portion here initially you will see some increase, but then after that sometimes you will see this flat region. That is the time when the polymer chains try to get straightened. So, this point here, you see this, first all the chains will try to get straightened, and once they are straight, then only they will try to take the load. Okay. So, that is this portion where they start taking the load. So, that is why you have a increase the strain hardening in polymers is this behavior on the right end of the graph. Okay. So, all the chains are convoluted, they are not in straight line. So, as you pull in the beginning, they will try to become straight, and once they become straight, then only they will really take the load applied. Okay. And this is one example of this is like the polythene bags which you use in shops and all that. You try to pull the plastic, the handle of the plastic bag or the plastic handle. If you try to pull, initially it will be very easy to increase the length of the plastic, but after some times it becomes very difficult. That is because initially when you pull it, the polymer chains try to get straight, and after some times they are already straight. So, now they start taking the load. So, it becomes more stronger. Okay. Hope it is clear. Now, in metals, strain hardening happens, and then in ceramics, the red graph here, the ceramics strain softening happens, and we will see how and why this is the reason. So, in ceramics, strain softening happens, which means from this point here the graph is going downward, whereas in metals strain hardening happens, where the point from this point the graphs go upward. Okay. Now, why it happens? Because in ceramics you might have a lot of cracks. As you see, this is a sketch on the top right of a sketch of concrete. You can say all these particles like aggregates, etc., and then you have small micro cracks, and then there you have some bleed related gap between the aggregate and the cement. All these are cracks or micro cracks in the concrete system, and you can see photo or micrographs showing that kind of cracks here. There is a crack here on the bottom right picture also, you can see cracks. So, because of these micro cracks which happen at this point, the micro crack happens, and then because of that it strain softening happens and not strain hardening. Okay. Now, again coming back to this stress strain, so we kind of covered this already. So, in case of ceramics, what will happen is the graph will kind of go downward from here itself. Okay. So, that is the typical behavior of ceramics or concrete, unlike the metals where the graph goes upward. Okay. Now, to summarize, we looked at variability in material properties, we looked at the characteristic value which is widely used for design purpose. We should not use the average values, but rather a value which is more conservative and which is the characteristic value. And then we also looked at stress strain behavior and various properties associated with the materials behavior like material properties, elastic modulus, Poisson's ratio, yield, strength, strain hardening, and necking and failure also we discussed. With that, I will close today. Thank you.